I'd like to talk a little bit about the human eye. I think personally it's one of the most interesting optical devices. I use mine all the time. Here is a schematic of an eyeball, and here's the basic parts of the eye here. So the light comes in, of course, this is electromagnetic radiation. The light comes in and it passes through the cornea. And most of the focusing happens at the cornea because it's got a nice curvature to it, and also because we have a large change in N. We have a change in N from air to this material here, this cornea, and then this liquid here, which is called the aqueous humor, and this is a fluid that's in here. So we get a large change in N from the air into this fluid, so we get a lot of bending of the light. Now, additional bending happens here at the lens, and this lens is actually something that we can deform. We have muscles that can deform the lens. So really, the eyeball is a two-lens system. And by deforming the lens here, using these ciliary muscles, then we are able to form a nice focus on our retina. On the retina, that's where the rods and cones live. And we're not going to get into a ton of detail on that. But we have different types of cells on our retina that sense electromagnetic radiation. We have the rods, which only sense black and white. They only sense bright or dark. And then we have the cones. And most people have three different types of cones, which gives us this rich color vision that most of us experience. Folks that have color blindness may have two types of cones, one type of cone, or even no types of cones. There's another condition, so-called tetrachromats, actually can have four types of cones in their eyeball. And it turns out that this is a sex-linked trait, and only females are capable of having four different types of cones on their eyeballs. I don't know if those people have a different experience or not. Anyhow, interesting stuff. So the lens here is able to deform, and that's what we call accommodation. So when your eye focuses, the ciliary muscle changes the focal length of the lens by changing the actual shape of the lens, and that's called accommodation. And that's what happens, if you're looking up real close here and reading a book or something, and then suddenly you shift to look at the far mountains, you're actually changing the shape of the lens in your eyeball so that that image continues to be focused on your retina. A typical eyeball is about 2 centimeters deep. And so we're going to present some equations for accommodation and for fixing different conditions, nearsightedness or farsightedness specifically. And through all of this, we are going to assume that everybody has a 2 centimeter eyeball. And so basically what we're assuming then, this is going to, as we go through, we're going to be using the thin lens equation. But what we're going to be assuming here is that our image distance is always 2 centimeters. And the reason we assume that is because, well, if we want a nice, well-focused image, then that image has to appear on the back of our eyeball. So maybe you have glasses or contact lenses. I am fortunate that I don't. Your prescription is measured actually in diopters. And so you may have a prescription of +1 or minus 1.5. And it turns out that what that is the power of your prescription. And it's really just 1 over the focal length. And we call it diopters. So it has a unit with a capital D, diopters. And 1 diopter is 1 meter to the -1, which is the same as 1 over a meter. So 1 diopter is 1 inverse meter, just a different way of writing the same thing. So this is how your eye accommodates for looking at distant objects versus up-close objects. When I'm looking at a distant object, the ciliary muscles are relaxed, and my lens is less curved. So in other words, it has less focusing power. It has a longer focal length in this position. This system of the cornea and the lens together has a longer focal length. And this allows us to focus on very distant objects. Now, when I look at something up close, however, then my ciliary muscles contract and they deform the lens, making it more curved, decreasing the focal length of the lens cornea system, and causing this close object now to focus nicely on my retina. A working lens can change about 8% to accommodate from seeing near objects and seeing far objects. As folks get older, we tend to lose our ability to accommodate, which is why basically everybody needs reading glasses at some point. So this will happen to all of us at some point. We will no longer be able to deform our lens and we'll need a little bit of extra help in the form of reading glasses. Reading glasses have a positive power. You can buy +1 or +2 reading glasses. That means they are converging lens and they help your eyeball to do this accommodation, which it is less able to do as we get older. Let's look at this situation here. So this is the thin lens equation right here. This is the thin lens equation applied to the eyeball viewing a very distant object. Our object distance is essentially infinity. So this is our 1 over s, is infinity. Remember that 1 over infinity, well, we can basically just say that equals 0. Right? If there's calculusy people in the room, we should probably say the limit as s approaches infinity goes to 0, but we don't have to get too worked up about that in physics class. We can go ahead and say 1 over infinity is 0. So this term goes away. Here we see 1 over, there's our 2 centimeters, right? And I'm going to remind you that that 2 centimeters is the length of a typical eyeball. So by putting this 2 centimeters here, we're saying we want this to focus on the back of the eye. Well, that then is the focal length of our eye, of our lens cornea system. So, for a typical eyeball, relaxed, looking at distant objects, it has a power of 50 diopters. A typical near point is 25 centimeters. What is the near point? The near point is the closest that you can get something to your eyeball and have it still focused. I'm in my 40s. I'm probably not too far away from needing reading glasses. At this point, though, that's about the closest I can get it and have it be real crisp. And that is about, what is that? About 26 centimeters. So, I'm not an optometrist, but, you know, ballpark, I still have pretty good accommodation. Okay, so a typical near point is 25 centimeters. Applying the thin lens equation to that scenario, we want to get as close as we can, 25 centimeters. We want to focus that image on the back of our eyeball, 2 centimeters from our lens, and that gives us a power of about 54 diopters. So there's that 8%, from 50 diopters to 54 diopters. That's what we want a healthy eyeball to be able to do, to change its focus, to change the power of the cornea lens system from about 50 diopters to about 54 diopters. Now, not all of us can do that. Some folks have eyeballs that are a little bit oblong in this direction, and some folks have eyeballs that are a little bit oblong in the other direction. So if you are farsighted, then it's because your eyeball is focusing the light behind your retina. So you're getting that fuzzy image because the light is focusing behind your retina. Your eyeball is, in effect, not long enough, or, to say it another way, the lens cornea system does not have enough focusing power. So, what do? Well, recall that when we are focusing on things that are very close, we have a power of about 54 diopters. And so we want to get to 54 diopters. That's what we want to do with our correction. And so we can do that by simply adding some corrective power plus the normal power of our relaxed eyeball. And so using this formula here, we can calculate a prescription. Let's do a quick example. Wilson's near point is 75 centimeters. What is his prescription? Okay, so we want to use this equation to figure out what our correction would be. So that will be our correction in diopters. So if we just run our calculator, then we get 2 0.66 diopters. Again, we get a positive value, a positive power, because this focus is behind the eyeball, and we need to bring that focus forward. So we need more focusing power. Another way to picture it is that this corrective lens that we're going to use here, it forms an image at 75 centimeters. So that's a way to visualize this. Like, we can think about it as just, okay, we're forming a focus here on the back of our lens, and that's true. But really, what we're doing here is we're setting up really now a 3-lens system. So now the system we're talking about consists of a glass lens, our cornea, and the lens inside of our eyeball that we can adjust, right? So this is really a 3-lens system. So one way of visualizing this then is that this single lens here, the single glass lens, forms an image. It forms an upright image at 75 centimeters, which Wilson can focus on. So that's just another way of visualizing it. It moves that object that you're trying to put right here, it moves the image of it out to here where you can focus on it. Just another way of thinking about the same effect. So that's how we correct for farsightedness. Some folks also see quite well close, but not so well far away. And so these folks are nearsightedness. The technical term for that is myopia. And in this case, these folks have a slightly elongated eyeball. Their lens is really too powerful. Even when your eyeball is completely relaxed, this focus is in front of the retina. And so it's a blurry image. What we really need to do then is we need to decrease the power of this lens in order to make the focus a little bit farther back. So folks who are nearsighted need negative prescriptions in order to move the focal point a little bit farther back. So here's another example. Michelle's far point is 300 centimeters. What is her prescription? So basically here, we just need to take away a little bit of the power from the lens cornea system. So in this case, for Michelle, her far point is 300 centimeters. So this is a person that cannot focus on anything that is farther than 3 meters, or about 10 feet away. So this person needs a negative prescription to help her do that. Let's see what prescription she needs. Negative 1 over 3 meters. Well, that is negative 0.33 diopters. So that is Michelle's prescription. And again, we can think about this in a couple of different ways. That negative focal length moves this point of convergence back until it's right there on the retina. Another way to picture it is it's a 3-lens system. Our lens in our eyeball, the cornea, and this glass lens that we are going to add to the outside. So we can picture this as taking a distant object and forming an image of it at a distance which this person can focus on. So we can visualize this situation here as being, it moves, and this glass lens here forms an image of an object at infinity. It forms an image at this person's far point. So for Michelle, we would want to form an image of a distant star at 300 centimeters, because Michelle can form another image right here on her